Welcome to week number 13 for ECE 111 Introduction to ECE. Today, we're going to look at problems you solve in ECE 320 Electronics 1, specifically how to solve nonlinear equations. Now, backing up a little bit, one of the reasons I really like electrical and computer engineering is it's very creative and it's very fresh. As long as technology keeps advancing, we got jobs, and jobs are kind of nice to have. You're never going to get stuck doing the same job day after day, year after year. Basically, as long as technology advances, anything I design today, you can do better 5 years from now because you're probably better engineers. But also, you've got better tools to work with. Case in point, motors. This is a motor. In my office, I've got one. It's about 18 inches long. 6-inch diameter, weighs 40 pounds, cost $2,500 back in 1990, with inflation about $5,000 today. That's a 1-horsepower motor from 1990, one of the finest pieces of 1990 technology you can buy. Well, today I can get the same functionality with a little quadcopter motor. A small 9-ounce motor costs $35, including the controller from eBay. If you think about it, anything I designed previously is obsolete today. Take that motor, replace it with the quadcopter motor. I've got much less weight. Weight's important. You cannot build a quadcopter with these DC motors. It weighs too much. You can build them with these motors. And that's the fun part of engineering. I now have 1 horsepower in a very small package. What do you do with it? Well, some of the things NASA's looking at is, can you get rid of the jet engine? Take a whole bunch of these motors, put them along the wing of an airplane. That way, if one of them fails, you don't care. You got 39 others. Plus, I can control the speed, reduce the turbulence, increase the efficiency of aircraft. What John Deere is looking at is getting power to different parts of the combine is really hard. I have to run camshafts, gears, pressure lines. That's difficult. It's really easy running 3 wires. With this motor to power it, all I need are 3 wires. The power to it. And you can almost build exoskeletons. If you ever saw the movie Aliens 2, where Sigourney Weaver's running around a big exoskeleton, you can basically do that. To give an idea of what 900 watts are one of those words. A typical bicycler will output 100 watts. A Tour de France, an elite cyclist, outputs 300 watts continuous. In a sprint, they can do about 1,000 watts for a few seconds. Well, this is a small motor the size of a DC battery that can equal the power of a world-class bicyclist. And not just for a couple seconds, it can do it continuous. That's pretty impressive. Now, kind of an idea of how these motors work. Let's go to this website. Kind of a fun website. It illustrates how motors work. Now, to start out, you've got Faraday's law. If I have a magnetic field, changing magnetic field going around a coil, or basically a fixed magnetic field and rotate the coil, what's going to happen is the magnetic flux being cut by that area changes. And that produces a voltage based upon the changing flux. This is an AC generator. Motors and generators are the same thing. So this is also an AC motor. Apply an AC voltage to the rotor and it'll spin. That's a single-phase AC motor. A DC motor looks like this. You add a commutator. What the commutator does is at the zero crossing, I flip the leads. So the net result is as I spin it, I get a DC voltage. Motors and generators are the same thing. If I do the same thing, apply DC voltage to the motor, it'll spin. Now this isn't actually how DC motors are built. The problem with this design is I have a very erratic torque, and so you're going to shake your teeth out. What they typically do in DC motors is they'll add, 6 commutators spinning around. So I just pull off the peak for one phase in the rotor, then another one switches in, then another one switches in, just gives you the peaks, makes a much more constant DC generator. And from duality, apply DC signal, I'll get a much more constant torque. Plus they take the rotor and twist it. So again, the voltage I produce is more constant, or the torque I get is more constant. Now the problem with the DC motor is I basically have 6 motors in one. I've got 6 rotors, one of them is being used at any given time. So the motor is now 6 times heavier, 6 times more expensive than an AC motor. In addition, when I switch out a lead, I have energy in that magnetic field. That energy has to go somewhere. And what happens is as the field collapses, the current goes to zero. The energy, well, it creates a current spike. The energy collapses, producing a spark. That spark will jam AM radio stations, so likewise DC motors have to have thick metal casings to keep the RF interference out, otherwise you jam all radio stations, jam all AM radio stations, and the FCC gets mad at you. So DC motors are extremely large, bulky. Part of the reason we want to use AC motors. There's a couple versions of the AC motors, scrolling down a little bit. A 2-phase AC synchronous motor would be like this. I have a sine phase up and down, cosine phase left and right. If I plot cosine versus sine, I get a rotating field. Kind of like what we did in week number 2. The rotating field then causes the rotor, which is a permanent magnet, to follow the rotating field. So this is a 2-phase AC synchronous motor. For the AC motors, the frequency of the oscillation is how fast the motor is spinning, and the torque is the lead angle. If the rotating field is slightly ahead of the motor spinning, I'm accelerating. If it's slightly behind, I'm decelerating. I'm using it as a generator. That's a 2-phase AC motor. The ones that are used by Tesla and basically all large motors are 3-phase motors. I'll have a 3-phase AC rotating field. And the nice thing about 3-phase is the currents, if you add them all up, they all cancel. And we'll cover that in week 15. You also cover that in energy conversion. But that's kind of how motors operate. So a problem with the motors is I have a battery trying to drive my motor. A DC signal will not drive an AC motor. I need to generate these waveforms. And for the bigger motors, I actually need 3-phase AC. You know, phase for voltage A, B, and C, and these are all slightly out of phase. Each one's 120 degrees out of phase from the other. That's the 3-phase AC. And if you look at these motors, I have 3 wires going to them. Right here, 3 wires. So I don't like the name 3-phase DC brushless motor. I don't think you can use the word phase and DC in the same sentence, but that's what they're called. Problem you have, if I want to run a 3-phase AC motor, like I want to use a small quadcopter motor rather than the great big one from 1990, I need to generate 3-phase AC signal. The battery is DC, the motor needs AC. How do I do that? On the other hand, if I want to use active braking, like I've got a car like a Tesla, I hit the brakes. The brakes don't actually kick in. What happens is motors and generators are the same thing. It'll suddenly take the motor and operate it as a generator, take the kinetic energy of the motor, convert it to electrical energy, and recharge the battery. Makes it much more efficient. So to make a 3-phase AC motor work, it's actually much harder. I've got to convert DC to 3-phase AC to drive the motor. I've got to convert 3-phase AC back to DC. And for the motor, frequency is speed, lead angle is torque. Again, the 3-phase AC motors are much harder to figure out, but if you can figure them out, I go from a 40-pound motor this big down to a little bitty D-size battery. I get much less size, less weight, which is a big deal. I get higher efficiencies, also a big deal. And it opens up a wide range of applications. Kind of think about it yourself. What could you do if you had 1 horsepower in a 9-ounce package? Well, actually today we have 1 horsepower in a 9-ounce package. It's a brushless motor from eBay. So the challenge you have in making these motors work is I need a DC to AC converter that goes from the battery to the motor, driving the motor, and I need to go from AC to DC. That's when I want to slow the motor down, active braking. How do I do that? Those are covered in electronics courses. 320 Electronics 1, 437 power electronics, and 438 electric drives. Basically, electronics is the heart of motors. And anybody using motors in the future is going to be using electric motors just because they're so much smaller, more efficient, more reliable. Along with more reliable, if you compare an electric car like a Tesla versus a gasoline car, there are 80% fewer moving parts. There's no clutch, no drivetrain, no transmission, no valves, no pistons. There's almost nothing to fail. So they're really cheap to maintain, really cheap to operate, and much more efficient. Anybody using motors in the future is going to be using electric motors, which is great for us. That means we got jobs. But they're kind of tricky to use, so I highly recommend these courses. A second area where, as long as technology keeps advancing, we got jobs, is lighting. Back in 1970, 2% we were using incandescent light bulbs. An incandescent light bulb is a whopping 2% efficient. There used to be a thing called the Barbie Easy Bake Oven. It's basically a metal box with a 25-watt light bulb in it. With it, you can make cupcakes, brownies, invite your friends over for tea, stuff like that. It's a 98% efficient heater, 2% efficient light bulb. And back in 1970, about 30% of our energy use went just to lighting. That's a huge number. Well, fast forward to today. Today, we have LED lights. If you look at pretty much all the street lights, they're LEDs. LED lights are currently 36% efficient, way better than 2% efficient. In theory, we can make them 80% efficient. We're not there yet, but working on it. And the amount of energy used to lighting has dropped down to 5%. That's a huge impact. That's coal plants you don't have to build. That's coal you don't have to burn. All sorts of advantages to switching to LED lighting. And LEDs are diodes. Those are electronic devices. That's jobs for us. Another reason to use LED lights. Provides jobs for electrical engineers. Now there is a problem with LED lighting. The LEDs are DC devices. They want to have a constant current. The power grid is 60 Hz AC. How do you convert AC to DC? Well, we cover that in electronics, but most solutions wind up like this. I have my AC voltage source right here in brown. I convert it to DC through some electronic circuitry. That's the blue line, pretty much a constant. The current, however, is no longer sine wave. The way the power grid is set up, I want to have sinusoidal voltages, I want to have sinusoidal currents. The incandescent light bulb did that. LED lights don't. For LEDs, this is what the current looks like. I get these big spikes. Those big spikes cause problems. They produce losses in transformers in the transmission lines. They can burn out the neutral lines for the utility. The challenge for you is, how do I come up with a AC to DC converter so that from the utility side, the voltage and the current is a nice clean sine wave, 60 Hz. From the LED side, the output current and voltage is a nice clean constant. Do that at 90 to 95% efficiency. Now, one way to do that is to have the AC drive an AC motor that drives a DC generator that drives the light bulb. That works. But with a motor generator, you're looking at maybe, 40, 50% efficiency, and a lot of size, a lot of cost, a lot of bulk. You're not about to put a motor generator in every light bulb. How do I do that with electronics? Currently, we don't know how to do that. Whoever figures that out is going to be worth billions. But all that is stuff that we cover in electronics. The heart of all those devices are electronics. Now, electronics is the analysis of circuits built with semiconductor elements. That includes thermistors, diodes, transistors, semiconductor relays, and MOSFETs. Almost all of these are nonlinear. That brings up the problem of, how do you solve n equations for n unknowns when you have nonlinear equations? That's kind of what we'll talk about today. So, starting out with the semiconductors. What is a semiconductor? Well, here's the periodic table of elements. If I go right here, these are the noble gases. These are elements where all the electron shells are filled. They don't want any more electrons. They don't want to give up any electrons. So these do not really interact with other elements. They're called the noble gases or inert gases. They're basically inert. Go one column left, I get the halogens. These are short one electron. If they had one more electron, they'd be a noble gas. All the shells are filled. So these are really greedy. They will steal, they'll rip away electrons from other atoms, strong oxidizers. If I go one to the right, I wind up over here. These are metals. Metals have extra electrons. They are more than happy to get rid of one electron because if they do, all the electron shells are filled. So the electron isn't actually free to move. I've got the nucleus with a plus charge. I have this extra electron I really don't care about. That electron is free to move throughout the crystal. I still need as many electrons as protons to keep it electrically neutral, but the electrons aren't really bound to any given atom. They're free to move. Moving electrons is current, so metals are very good conductors. And you have all sorts of different metals. Right here are the semiconductors, like silicon. It's neither a metal or a nonmetal. In column 4, what the crystals look like, it's actually a tetrahedron, but drawing it on two-dimensional paper, kind of looks like this. Any given silicon atom has 4 electrons in its outer shell. I want 8 to fill all the covalent bonds, to fill up my shells. So what it does is it has 4 neighbors. With each neighbor, it shares 1 electron in a covalent bond. So the net result is the silicon atom sees all its covalent bonds are filled. It doesn't want any more electrons, doesn't want to give up any electrons. So at low temperatures, silicon is an insulator. There's no free charges to carry a current. If I heat up silicon, however, some of the electrons will escape their covalent bond with thermal energy. When it does it, that electron has got no place to go. All the other covalent bonds are filled, so that electron is free to move throughout the crystal and carry current. In addition, I have a hole. A hole is the missing electron. If this electron escapes its covalent bond and moves over here, now this becomes a hole. If this electron then escapes its covalent bond, moves over here, and fills it, here's the hole. So holes move and electrons move, and that's important. For semiconductors, I've got 2 ways to carry charge, electrons and holes. A hole isn't actually a physical particle, but it behaves like a plus charge. It's a missing electron, like a double negative. So I really have 2 types of charge carriers, electrons and holes. With doping, I can control which type of charge carrier is dominant in the semiconductor. If I dope the silicon with boron, then what happens is boron has 3 electrons in its outer shell. It's missing that 4th electron. So what happens when I replace a silicon atom with a boron atom, I wind up with extra holes. And what that does is I now have a bunch of holes in the semiconductor device. Almost all the charge carriers are electrons. If a thermal electron is created, say I create an electron and a hole, the electron is quickly swallowed up by all the extra holes, so almost all the charge carriers are holes. Conversely, if I dope the material with phosphorus, phosphorus has 5 electrons in its outer shell. 4 of them fill the covalent bonds. That extra electron really has no place to go. It's electrically bound to the phosphorus due to charge, but it's not bound to any particular atom, so it's free to move throughout the crystal. It's free to carry current. In this case, if I have a thermal electron, so here's an electron and a hole, that hole quickly gets swallowed up by the extra electrons, and almost all the charge carriers are electrons. So this would be called p-type silicon. Almost all the charge carriers are plus charges, holes. This is called n-type silicon. And that's what's unique about semiconductors. I've got 2 ways to carry charge. With metals, there's only 1, electrons. Semiconductors have 2. What that does is I can start building different devices. If I have 2 pieces of semiconductor up against each other, p-type and n-type, I get what's called a diode. I put 3 of them together, I get a transistor, a BJT transistor. Put 4 of them together, I get a semiconductor relay. 3 of them together with a substrate is a MOSFET. So what's really unique about silicon is there are 2 types of charge carriers, electrons and holes, and with that, I can build various devices. Now the first one, the diode, acts like a valve. The symbol for a diode is this. It's an arrow kind of reminding you that current can flow in the direction of the arrow, left to right, anode to cathode, but it doesn't flow backwards. If you build a circuit like this, throw it in Circuit Lab, then what happens is if the input is a voltage source, the blue line, the voltage at V1 becomes the red line. When the voltage is positive, the diode turns on, and V1 equals V0 minus a small drop across the diode right here. Once I try to make V1 negative, or V0 negative, and try to make current go backwards, the diode turns off, and it blocks all current flow, so V1 is just 0. So this is a nonlinear element. When it goes forward, it allows current to flow. When it goes backwards, it doesn't. That's nonlinear. That's what makes diode circuits so hard to analyze. Some of the things you can do with diodes. You can use them to control the direction of current, and I can also use them to build LED light bulbs, like we mentioned before. And if you look at the efficiency of LED lights, this is technology from, probably goes back to Edison, 1903. They're about 2% efficient. With constant work, we're able to get them up to 5% efficient. That's not very good. This is why incandescent light bulbs are banned in Europe. In the United States, we are trying to ban them just because they're so bloody inefficient, but it's hard to get anything passed in the US. We did try to ban them, but then they were sold as heating elements. It's a 2% efficient light bulb, 90% efficient heater. So technically, it's actually more correct to call a light bulb a heater. But anyway, these are the incandescent light bulbs using technology from 1900. Now you probably don't remember it. Some of the old movies like Dragnet, the lights went from being kind of yellowish to a bluish. They're mercury vapor lights. They're 14% efficient, way more efficient than incandescent light bulbs. City switched over to mercury vapor lights, kind of the bluish light bulbs, because if I can use 7 times less energy, that's a big deal for a city. Consider how much energy these cities use for their street lighting. The sodium light bulbs are kind of the yellow lights. That was the next phase, a little bit more efficient. I go up to 34% efficient. The LED light bulbs are currently 36% efficient. I guess the CFL came in. CFLs were like the year 2000. Those are 26% efficient. Both these use mercury, which is a problem. It's a poisonous substance. LED light bulbs don't use mercury or anything toxic. It's just silicon with a little bit of boron or phosphorus. They're 36% efficient, and almost all street lighting is switching towards LED lights as a result. In theory, LED lights can be 80% efficient. But we're not there yet. We're getting there. So that's one thing you can do with diodes. You can build LEDs. If I have 3 types of silicon together, NPN or PNP, I get a transistor. Transistors can act as electronic switch. That allows a small device, think of something wimpy like a microprocessor, to turn on and off something big, like a motor or an LED. It allows a small device to drive a motor forward and backwards, using a different circuit like an H-bridge. And this is the heart of AC to DC converters. If this is a motor, I want the current to go back and forth. To get the current to go right, I would turn on T1 and T4. Then the current goes forward. If I want to go backwards, let's change the color. If current goes this way, I turn on T3 and T2. So by switching between these two, I make the current go left, right, right. I have an AC source. Again, that's studied in Power Electronics 437 and 438. Another use of transistors. Transistors are current amplifiers. One problem with transistors, this is what you cover in 321 analog electronics. A problem when using them as an amplifier is they dump voltage. So if I have a 40-volt source, I want to get some of it to a speaker. If the voltage to the speaker is supposed to go up and down like this, say sine wave, the excess voltage is dumped by the transistor. Well, current times voltage is power. If I do that, it's going to get hot. So for analog electronics, I have to have a way to dissipate the heat. That's what these are. This is a transistor, and it's designed to be attached to a heatsink, a big aluminum plate, to dissipate that extra heat. And if you look inside a stereo, typically you see 4 transistors. This is the push, positive voltage for the NPN, the pull for negative voltage. Again, speaker goes up and down, so I get a push-pull amplifier. One of them goes push, NPN, other one's pull, PNP. And here's my second channel. So there's my left channel, there's my right channel, push and pull. So transistors are also used for amplifiers. That's covered in 321 analog electronics. MOSFET is a semiconductor device. If I have an N channel, P channel, N channel, normally there's no current flow because somewhere in here is a reverse bias diode, a PN junction going backwards. If, however, I apply a plus voltage to the gate, that will attract electrons to the surface. And now what I have is an N channel. That's like a switch. I can turn it on with a plus charge, and now conducts. I can turn it off by discharging it, turns off. I've got my on-off device. That's the heart of a CMOS device, basically computers. So those are all things that you study in electronics. For this class, let's look at just a very specific example. Let's just look at a diode. Now, a diode is a nonlinear element that acts like a valve. It has high resistance when I try to have current go backwards. If I try to make current go forward, it has low resistance. So it's like a variable resistor. Allows current to only flow one way. The symbol for a diode is kind of a reminder. Current goes anode to cathode, left to right. It doesn't go backwards. It's not very well. The characteristics for a diode are nonlinear. For a resistor, it's V equals IR, a nice straight line. Diodes are different. The voltage is the log of current, or the current is exponential in voltage, and here's kind of what it looks like. Again, for a resistor, it would be a straight line. For a diode, it looks like this. That makes diode circuits really hard to solve. With a diode circuit, I have to solve nonlinear equations. So that's what makes electronics such a hard course. You're probably used to solving linear equations. Back in Math 129, you solve n equations to n unknowns. In algebra, you're solving linear equations typically. Anytime you have a circuit with just resistors, capacitors, and inductors, you're looking at a linear circuit. With linear circuits, I wind up with n equations, n unknowns that are linear. And then I can use linear algebra and Matlab. In electronics, we're dealing with nonlinear circuit elements, like diodes, transistors, MOSFETs. I can still come up with n equations for n unknowns, but they're no longer linear. So likewise, the techniques used in linear algebra, like using matrices, matrix inverses, no longer work. I need a different tool. That's what makes electronics so hard. And also, nonlinear elements behave kind of weird. A resistor is a linear element. If I have 100 milliamps feeding 2 identical resistors, they'll share the load. Each one gets 50 milliamps. If there's a tolerance, they're both these 100 ohms, give or take, say 5%, it'll still be close to 50 milliamps. Diodes don't do that. They're nonlinear. If they're exactly the same, they'll share the current, but due to tolerances, the diodes will be slightly different. Because of that slight difference, one diode will carry the brunt of the current versus the other. So likewise, if I have 2 resistors, they can't handle the power, put them in parallel, do that to diodes, that's not going to work. If I put them in parallel, this takes the brunt of the current, burns out. Now this takes all the current and burns out. This is how you burn out diodes. In addition, nonlinear equations are hard to solve. So for example, if I have this circuit, this is about as simple as you can get. If I were to write the equations for the circuit, I'll have 2 equations, 2 unknowns. My two unknowns are the current and the voltage. Well, I've got the diode equation. Given the voltage, I can find the current. It's nonlinear. I've got the second equation. Doing the current loop, I have minus 10 plus 100 ID plus VD equals 0, or bring the minus 10 right. 10 volts is equal to 100 times ID plus VD. Two equations, two unknowns, solve. That sounds simple, but it's not because these are nonlinear. Well, with two equations, two unknowns, I can graph them. This is called load line analysis or graphical solution. I can take the first equation, the diode equation, and plot current versus voltage. Take the second equation, plot current versus voltage, and where they intersect is my solution. That's a graphical way to solve two equations, two unknowns. I can solve numerically. So this is where Matlab comes to the rescue. What I'm going to do is come up with a Matlab script. That's this guy right here. I'm going to guess the voltage across the diode, and I want the cost to be 0 when I'm at the right answer. So what I'm going to do is I'm going to guess the voltage. Once I know the voltage, I know the current through the diode from the first equation. Once I know the current and the voltage, this should add up to 0. If I did it right, E1 is 0. If it's wrong, E1 is no longer equal to 0. Make J E squared. Then if I have my voltage versus J, there's a minimum. The minimum is going to be equal to 0. That's the point where the current balances. That's the voltage that makes the current balance. So now use fn search to find out what's the minimum of this function. I'm going to guess my voltage, like is the voltage across the diode 2? Guess again, then fn search will iterate and eventually find the solution. So for example, here's that same routine. Let's make sure I'm in the right directory. This is a function. I can't run functions. I can call a function, but I can't run it. From the command window, I can sit there and say diode 1, is the voltage across the diode 2? So just for fun, I'm also displaying my guess and the log base 10 of the error of J. 2 was an absolutely horrible guess. Is the voltage across the diode 1? That's better. Is it equal to point? Better yet. So you can guess again, or use fn search. I want to minimize this function, and there's my initial guess. And what it does, it guesses. It eventually says, there's my answer. 0.8854 volts, and there's the sum squared error, 2.9 times 10 to the minus 9. Not exactly 0, but pretty close. And tell you what, let's slow this down just so you can watch it. Give it a different initial guess, like 3 volts. It's guessing, trying to make the right-hand column as negative as possible. Voila, there's your answer. Another way to solve is Circuit Lab. Build a circuit in Circuit Lab and tell it to solve, and it's going to tell you the voltage and the current. In Matlab, I got 0.8256. In Circuit Lab, it's 0.7827 volts. That's typical in electronics. Each of these assumes a slightly different model for the diode, so I'll get a slightly different answer. If I build the circuit, I'll get a third answer. When I build it, again, Circuit Lab uses a model, Matlab used a model. All models are slightly inaccurate. The real answer is what you build in lab. I typically get 3 different answers. Matlab will give one answer, Circuit Lab gives a second answer, in the lab I get a third answer. They should all be close, a little bit different than close. And that's kind of what I use when I grade. If all 3 answers are exactly the same, you didn't do the lab. If all 3 answers are close, but a little bit different, that's really expected. So that's the simplest circuit you can come up with, and that really wasn't that easy. A harder circuit. Given a 3-diode circuit, Now find the voltages and currents. Now we're going to do the same thing that we did before. I've got 3 unknowns, V1, V2, V3. Actually, I have 6 unknowns, V1, V2, V3, ID1, ID2, ID3. Come up with 6 equations, 6 unknowns. Well, 3 of them I can come up with pretty easy. That's just the diode. Well, I guess approaches to solve. So here's the problem. I've got 6 equations, 6 unknowns. How do I solve? Load lines aren't going to work because I don't know how to draw in 6-dimensional paper. But numerical solutions, like Matlab, still work. So I need to write 6 equations for 6 unknowns, then solve using fmin search. Again, I can't solve using linear algebra techniques because these are nonlinear equations. So first off, let's come up with the first 3 equations. Those are the diode equations. If I just look at diode 1, all diode 1 sees is anode to cathode, V1 versus V2. So take your diode equation and plug in, this is your VD, anode to cathode. This diode sees V1 minus V2. Doesn't care about anything else in the circuit. Diode 2, anode to cathode, sees V2 versus V3, this guy. Diode 3, anode to cathode, sees V3 versus ground. And these are going to change depending upon where the diodes are in the circuit. Just think about each diode by itself. The diode doesn't know or care about anything else in the circuit. All it sees is anode to cathode. What are those 2 voltages? So that gives me 3 of the 6 equations I need. The other 3 equations are your voltage nodes. At node 1, the currents have to balance. So all these have to add to 0. And when I do the current through the diode, just use ID1. So at this point, this will be V1 minus 10 over 100 plus ID1 plus V1 minus V2 over 200 plus V1 minus V3 over 300 plus V1 over 400 equals 0. This equation. Diode 2, current up, current down, current right equals 0. Current up is minus ID1, current down is plus ID2, current right is V2 minus V1 over 200. At diode 3, at V3 I mean, current up, current down, current right add to 0. Current up is minus ID2, current down is plus ID3, current right is V3 minus V1 over 300. And when you take electronics, this is typically where you stop at the test. Write the equations, because these are hard to solve. On the homework, you can actually solve. In addition, I'm oftentimes accused of being tricky, which I think this is a compliment. What I'll do on tests is once you see this circuit, you know it, you got it down really well. Change it. Make this a resistor and put the diode right here. Now write the equations. Again, all the diode cares about is anode to cathode. So if I did this, the voltage across the diode is V3 minus V1. And then I've got to sum the currents to 0. To solve, again, these are nonlinear equations. I have this set of equations and these equal 0. To solve, what I'm going to do, I'm going to guess V1, V2, and V3. Once I know the voltages, I can find the currents. I can then sum all these to 0. If I guess the voltage is right, they'll add to 0. If I'm wrong, it'll be non-zero. Call that E1, E2, E3. Now return the sum squared error and minimize j. The solution that makes j equal to 0 is the correct answer. So in Matlab, what I'll do, I'll have this function. I'm going to pass the vector z. Parsing it, that means z is v1, v2, v3. I've got the characteristics for the diode. That varies with each diode. Once I know the voltages, I can find the current through the diode. And this depends upon the circuit. For this circuit, anode to cathode is V1 minus V2. Anode to cathode, V2 minus V3, V3 minus 0. Then I write my voltage node equations. All these should add to 0, if correct. If I'm wrong, they'll be non-zero. Call that E1, E2, E3. return the sum squared error. Now in Matlab, I can do that. Here's my function. If I say diode 3 is the voltage 1 volt, 2 volts, 3 volts. And it says this is the sum squared error, 10 to the 33rd, saying that was a really bad guess. Okay, let's try 3, 2, 1. That's better. Let's try 3, 2.9. Worse. So guess again, or let MATLAB guess for you. Let's minimize this function, diode 3. Here's my initial guess. And there's my guesses on V1, V2, V3, the log base 10 of the error. I want that to go as negative as possible. And it either kicks out because it found the answer, or it couldn't do any better. If I repeat, make this the answer from the previous iteration, let it keep going, can I do better? That's pretty much the same answer. So this is pretty close to 0, saying it found the answer. And here's your voltages, V1, V2, V3. In Circuit Lab, I can check, build the circuit, and tell it to solve. And what Circuit Lab is doing is exactly the same thing you just did in MATLAB. It's iterating, trying to figure out what voltages make the currents balance. You always have to have conservation of current. Current in equals current out. The voltage will be whatever it takes to make the currents balance. And in Circuit Lab, it came up with 2.3, 1.5, 0.77, comparing 2.3 versus 2.43. Yeah, pretty close. 1.5 versus 1.6, 0.77 versus 0.81. Again, it'll be a little bit different. That's typical in electronics. When you take electronics, I will then go out and build a circuit and measure the voltages myself. In that case, I'll have a third answer. Close, probably a little bit different, but close. If you get an answer that's way, way off, what probably happens is you put the diode in backwards. That gives you a different circuit. A different circuit has a different answer. So here's a handout. Write the, I guess it's going to be 1, 2, 3, 4 nodes, 4 knowns. Give me 8 equations for 8 unknowns for this circuit. Now let's start with the diodes. Give me the 4 diode equations. So starting out with the diodes, let's do it this way. I know that for the first diode, using this equation right there, ID is 1e minus 8 times the voltage drop across diode 1 is V2 minus V3, anode to cathode. V2 minus V3 slash 0.052 minus 1. ID2, that should have been 1. ID2 is the same thing, 1e minus 8 times exp of voltage drop across the second diode is anode to cathode, V3 minus 0. Third diode, ID3 is 1e minus 8 times exp of the voltage drop across the diode, anode to cathode, is V4 minus 0. The fourth diode, anode to cathode, is V4 minus V1. So that gives me 4 equations, 4 unknowns. Those are the diode equations. Now to write the node equations. At node 0, I know that V0 equals 10. At node 1, these currents have to add to 0. So that's going to be V1 minus V0 over 100 plus V1 minus V2 over 200 plus this current plus V1 minus V4 over 300 plus this current. That current is minus ID4. Minus ID4 plus V1 over 400 equals 0. That equation. Node 2. Let's do that in a different color. And node 2, current up plus a current down equals 0. Current up is V2 minus V1 over 200. Current down is plus ID1. That's everyone. That's got to be 0. Third equation at V3. Let's do that in orange. Current up plus current down equals 0. Current up is minus ID1. Current down is plus ID2 equals 0. Basically, ID1 equals ID2. Node 3. Running out of colors here. Green. Node 4. Current up, down, and right equals 0. Current up here. V4 minus V1 over 300 plus current down is ID3. Current right is ID4. Is 0. And that's it. Okay, so this is my 8 equations, 8 unknowns. 4 for the diodes and 4 for the voltage nodes. So in summary, in electronics, you deal with nonlinear circuit elements, thermistors, diodes, transistors, MOSFETs, semiconductor relays, and so on. Voltage nodes and current loops still apply. Using voltage nodes and current loops, I can write n equations for n unknowns. However, they're going to be nonlinear equations. To solve nonlinear equations, fmin search is really useful. Basically, Matlab comes to the rescue once again. With fmin search, I can solve n nonlinear equations for n unknowns. I can solve for just linear equations like we did before, and I can solve nonlinear equations like we did here. So that should be enough to get you through the homework for this week. And that's lecture number 13 for ECE 111.